Check it.
Okay, welcome back. Today we're going to be solving systems of equations with 3 variables. Now, we've solved systems of equations with 2 variables, and that looked like this. Okay, this is a system with 2 variables. You notice you have an x and you have a y. Now, the idea here is that if you tried to solve one of these equations, let's say you wanted to solve just 3x minus y equals 15, you cannot solve an equation with 2 different variables in it. You can solve this, 3x plus 5 equals 17 or something, right? One variable, you're fine. You can even solve if you have 3x squared plus 2x plus 5 equals 17. Still, just x, just x. This is an x squared, but it's all one letter, that's the point. And you can eventually solve for x if you want to. But if you have 2 different letters, 2 different variables completely, in one equation, you cannot solve for x. I mean, you can get the x by itself, but then your answer, this will be x equals, and the thing on this side will have a y in it. So it won't be a real answer. It won't be like x equals 12 is your answer. It'll be like x equals 12 minus 2y or something. So you cannot solve an equation that has 2 variables in it. However, if you have 2 variables and 2 equations, then you can get a value for x and a value for y. So the number of equations has to match the number of variables. And we're going to be doing it where there's 3 variables. So in order to solve a 3 variable system, you're going to need 3 equations. Let's take a look at one of the questions here. Like here, we have an x, a y, and a z. Well, you cannot solve a 3 variable equation unless you have 3 equations. 1, 2, 3. Okay, with these 3 equations, there's a trick that we can use called double elimination where we can solve. Okay, now if you remember regular elimination, this is lesson 3-2 here. You can go back and watch the video on that. 3-2 day 2 actually. 3-2 day 1 was something called substitution, and day 2 was called elimination. Anyway, go back and watch that video if you haven't already watched it. For elimination, the idea was that you had 2 equations and you were going to try to eliminate one of the variables by adding the equations together. Now in this case, it's really, really simple because you can see the y and the negative y here are going to cancel out if you add, and this becomes 5x. These cancel out. This becomes 25, and now you have x equals 5. Right? Piece of cake. And now that you know what x is, you can plug in 5 for x in one of the original equations, 3 times 5 minus y equals 15, and you could figure out what y is. And now you have your x and your y. And what that really was but these 2 are equations of lines, and you were figuring out where the 2 lines intersect. They intersect at x equals 5 and y equals some number that I didn't bother solving for right now because that's not what we're doing. But with a 3-line system, you're going to need 3 equations. Okay, so let's get into it here. You have 3 equations and 3 variables. And unlike elimination where you just add together 2 equations, here you have 3 equations. So what do? Well, the first thing you do is understand that you can only work on 2 at a time. You can't add all 3 together. That usually does not work. So we're going to focus on either taking, I don't know, the top 2 and working on that, or maybe the bottom 2. Or we might even take the top 1 and the bottom 1, okay, this one and this one, and put those together and see what happens if we add those together. So how do you choose? Well, here's the thing. You have to decide which one of these letters, x, y, or z, looks the easiest to you to eliminate. So what I normally do is look for the smallest least common multiple. What's the smallest number that 2, 3, and 5 will go into evenly? Well, 3 and 5, you need 15 for them to both go in evenly, but 2 doesn't go into 3 or 15, so 30. This would require you to get all of them up to 30. How about here? 4, 5, and 3. Yeah, you'd need a 20 to get 4 and 5, and then you'd need a 60. It looks like I'm just multiplying them, but the fact is it's not just multiplying. Here, you need 5 and 2 to go into a number. It would be 10. Okay, it looks like the Z is the letter that has coefficients, meaning the numbers in front of the letters, that are the smallest that will get you to have all of them be the same thing. So that's the trick that I use to make these as easy as possible. Go with the letter that has the smallest least common multiple. Okay, the least common multiple is the number that they all go into evenly. So I'm going to try to cancel out all the z's. And once I do that, I'll have nothing but 2 variables, and I know how to solve a 2 variable system using elimination. And that's the trick we're going to do here. So let's take the top 2 equations and put them over here. And you know what? Let's just save some time and do the bottom 2 while we're at it. Okay, So the top two equations I've put right over here, and the bottom two equations I put over here. So I've already decided that I'm going to eliminate the z for both of these sets of equations here. The reason being that they have the smallest least common multiple. So how do I do that? Well, it's just like regular elimination. Let's just focus on this one in the middle here first. How do I get the z's to cancel out? Well, once again, you're going to look for a least common multiple. That least common multiple between 5 and 2 is going to be 10. So I need to make this a 10z and this a 10z. All right? How do I do that? Well, I do that by multiplying the top equation all by 2 and the bottom equation all by 5. That'll make this a negative, there's already a negative here, negative 10z, and this will be a positive 10z, and those z's will cancel out. That's the idea behind elimination, to get a least common multiple. So, of course, you can't multiply the 5z by 2 without multiplying the whole equation. So we're going to do that. Multiply everything here by 2, and you get 4x plus 8y minus 10z, which is what I wanted, equals 36. Don't forget to multiply both sides, by the way. So everything by 2. And now the bottom equation, everything by 5. So 5 times negative 3x is negative 15x. 5 times this is 25y. 5 times this is positive 10z. And you can see these are going to cancel out. That was the point of doing this. And then 5 times 27 is negative 135, negative 27. So now if you add these, what happens? Well, you can see the z's get eliminated. And now that the z's have canceled each other out, I can add together what's left. 4x minus 15x is negative 11x. 8y plus 25y is 33y. And 36 minus 135 is negative 99. Now, is that a solution? Is that an answer? No, it's not. It's got two variables in here, so I cannot solve this. But I am going to use this. But watch what I'm going to do. Now I'm going to go over to the other two equations, the bottom two, and I'm going to get rid of the z's as well. And that's also going to produce an x and y equation, but then I can put those two equations together and do regular old-fashioned elimination like we learned in Algebra 1. So let's take a look. We want to get rid of z again. What's the least common? This is 2z and this is 1z, by the way, even though we don't have to write the 1. So what's the least common multiple of 2 and 1? A number they both go into evenly. Yeah, they both go evenly into 2. So the least common multiple is 2. So how do I get these to both be a 2z? Well, this one's already a 2z, so I don't have to multiply it by anything. Leave the top line alone. So I can just copy it down here. However, the bottom needs to be multiplied by 2 all the way across. So I get this. So you can see that these are going to cancel out when I add these two equations together. And what's left? Well, negative 3x and negative 10x is negative 13x. 5y plus 6y is 11y. And these are going to give you negative 61. And once again, this is not a solution by itself, but watch what I'm going to do now. We now have two equations with two variables. And when you have two equations and two variables, you can solve this with elimination, where we have this equation right here and this equation right here, and we can solve this using good old-fashioned elimination like from Algebra 1. So let's take a look here. Which of the two variables have the smallest least common multiple? Well, let's see, 11 and 13, they're both prime numbers, which means that they have no factors in common, which means the only way to get a least common multiple is to multiply them. And 13 times 11 is 143. So that's got a least common multiple of 143. On the other hand, 11 and 33, they both go into 33, don't they? 11 goes into 33 and 33 goes into itself. So that's the least common multiple there, and that's a lot lower than 143. So my goal is to make them both 33s. Now this one's already a 33, so I don't have to do anything. Question is, how do I get the bottom to become a 33? Well, that's pretty simple. Just multiply by 3, and 3 times 11 is 33. So that's the game here. We're going to do regular elimination now. This is from Algebra 1 now. The top line doesn't have to change because it's already good. The bottom line becomes negative 39x plus 33y equals negative 183. Problem is they're both positive here. So in case you weren't paying attention, you try to cancel these out. That doesn't work. So I actually made an intentional mistake here. You're not just multiplying by 3, you need to multiply by negative 3. Why is that? Because it's not enough that they both become the same number, 33. One of them has to be positive and one of them has to be negative, and it doesn't matter which is which. So if I multiply by negative 3, what changes? Well, this becomes a positive 39. so no more negative there. This becomes a negative 33y, which is what we need, and this becomes a positive 183. Now that is ready for elimination, and you can see these eliminate beautifully. So what do we get when we add? We get 39 minus 11, which is 28x. These are gone. And what's 183 minus 99? It's 84. Divide both sides by 28, and we get x equals 3. So we have one of our three variables now, but we're not done till we find all three variables. So we have the x. How do you find the y? Well, I could take that x equals 3 and plug it back into the original problem like we used to do back in regular elimination, but knowing that x is 3 leaves us with two variables. So that doesn't work. You're not going to plug into the 3 variable system when you only have one variable figured out. So what you're going to do is go back to where you had 2 variables, which would be here. Go back to this system here. Take one of, and it doesn't matter which one of those 2 equations and plug in what you know, which is x equals 3. That has now been discovered. You know x equals 3. And if you plug in x equals 3 here, you only have a single variable and you can solve for that. So let's go with the bottom equation here. The bottom equation is negative 13x. I'm leaving a blank space here for x, plus 11y equals negative 61. And I know that x is what? X is 3. Put that in there. So that becomes negative 39 plus 11y equals negative 61. And you can see this equation only has one letter in it, and I can solve. Well, I'm going to add 39 to both sides. This goes bye-bye. This becomes 11y equals negative 22. Then divide both sides by 11, and we get y equals negative 2. 2 down, 1 to go. Now that I know x and y, I just need to find z. Now, how do I find z? Well, now we do have to go back to the original problem with the 3 variables and choose one of those equations. We come back here, way back here, choose one of these 3 equations. It doesn't matter which one, whichever one looks easiest. I'll just choose the top because the top, I don't know, has less negatives, or I don't know, whatever. So it's 2x, I'm going to put a blank where the x goes, plus 4y minus 5, the z that we're looking for, equals 18. And we said that x was 3 and y was negative 2. And now you can see we have an equation with only one variable. We can solve for z now. So what does this become? This is 6 minus 8 minus 5z equals 18. 6 minus 8 is negative 2. So negative 2 minus 5z equals 18. Okay. And now it's just an algebra 1 question here. Negative 5z equals positive 20. Z equals negative 4. So I have x, I have y, I have z, but I'm not done till I write this in the correct format. When you find the answer to a system of equations, you have to write the answer as an ordered pair, something comma something. Well, for a 3-line system, it's something comma something comma something, and just like with the 2-line systems, it has to be alphabetical. So if you're dealing with R and S, it would be R comma S, not S comma R. Here we have something simple, X, Y, Z, right? So just make sure when you write your answer, it's in alphabetical order, X first, which is 3, y, which is negative 2, and z, which is negative 4. And here's what your answer looks like right there. So that's a solution to a 3-line system. Okay, this next example is also a 3-variable system, and you have 3 lines. But if you look at it, you notice that not every line has every variable. Like for instance, this top line only has x and y, no z. This one has no x. This one has all 3. So how do you deal with this? Well, any variable that's missing, just think of it as being 0 for a coefficient, meaning this is x plus 2y and no z, so we'll rewrite it as x plus 2y plus 0z. And this one here is missing an x, so it's 0x because there's no x, plus 3y minus 4z equals 25. And this one's fine the way it is, so I'll just copy it. Now I've rewritten my 3-line system so that I have all of the variables showing here. And now I look for my least common multiple. Which one of these is going to have the easiest time getting rid of variables here? So something interesting happens here. In order to find a least common multiple, you can't use one of the letters that has a 0 in front of it. The reason being is, let's say we're working on the top 2 equations here. We want them to have, this is a 1x, this is a 0x. What's the least common multiple between 1 and 0? It's 0. So unfortunately, there's nothing I can multiply, unless I multiply by 0, which will wipe out everything. I can't get these to be the same number. It's impossible. That's the reason why you don't want to use the variables that have a 0 coefficient, that are missing, so to speak. So the only one that I have, the only choice I have here is the y's. The y's are all here because I can't use this 0z here. I can't use the 0x here. I can use the y's here. So this is kind of forcing my hand. What is the least common multiple between 2, 3, and 6? 12. 2 goes into 12, 3 goes into 12, 6 goes into 12, and that is the smallest number they all go into. No, that is not true at all. 6 is the least common multiple because 2 goes into 6, 3 goes into 6, and 6 goes into 6. So least common multiple, not just any common multiple, the least common multiple is what you're looking for. And this has a least common multiple of 6, which is actually pretty low, so I think I'm in good shape here. So my job is to get the y's to all become 6's and to cancel each other out by doing this 2 lines at a time. So let's do that. Let's take the top 2 equations and make a system out of them. Let's take the bottom 2 equations and make a system out of them. All right, so once again with the color coding, here are the top 2 right here, and here's the bottom 2 right here. And now let's take a look. We want to get rid of the y's, we said, right? So let's just kind of zoom in here and focus on one of these at a time. We want the y's to cancel out. The least common multiple between 2 and 3 would be 6. Okay, that's the smallest number. They both go into evenly. To make this a 6, I have to multiply the top equation by 3. That'll make this a 6y. To make this a 6y, I need to multiply the bottom equation by 2. The problem is now they're both positive 6y, and they're not going to cancel out. So one of them has to be negative. So I'll make the bottom negative 2. Let's see what we get. Multiply all this by 3. We get 3x plus 6y. This is still 0z. See what I'm talking about? You cannot actually use this for anything. Equals 36. Don't forget to multiply the other side as well. And now negative 2 times 0 is still going to be 0, which is why you can't use that. This is going to be negative 6y, which is exactly what we need it to be. This is going to be positive 8z, and this is going to be negative 50. So when we add these together, what do we get? Those cancel out, which is exactly what we want to happen. And what we get here is 3x plus 0x is still 3x, plus 8z equals negative 14. Now, that's not an answer. That's a two variable equation. We're going to need another equation with both x and z in it to be able to continue. So come over here, get rid of the y's on this equation here, and you'll have what you need. So once again, we have 2 y's here. What's the least common multiple of 3 and 6? Also 6 again, right? So we need this to be a 6y. We need this to be a 6y. This is already a 6y, so let's leave that one alone. To make this a 6, we need to multiply the top by 2, but we also need something to be negative, so let's multiply it by negative 2. Okay, so multiply negative 2 across the top here, you get 0x, because that's still 0, minus 6y plus 8z equals negative 50. All right, the bottom we don't have to touch because the bottom is already good, and you can see that these are going to cancel out. So what do we get? What's 0x plus 1x? Still just 1x. Remember, 0 anything is the same as if it's not there. So you have to just regard this as not even being there. So nothing plus x is x. And this is gone. This is going to be 9z. And this is 20 minus 50, which is negative 30. So we zoom out. We see we have 2 equations with 2 variables. And because we thought about it ahead of time, they're both x and z, x and z. So we can put them together into a single system now. And that is a system we can solve with elimination. So we look at the system here and we decide, are we going to go after the x's or after the z's first? Once again, look for the least common multiple. This is 3 and 1. What's the lowest number that both of these go into evenly? 3. That's the least common multiple there. What's the least common multiple of 8 and 9? 72 is the smallest number they both go into. So I would definitely go for the x's. It's going to be easier. You can do the 72, that's fine, just more work. So I'm going to go with these here. Now, to make both of these into the least common multiple, which is 3, I need to leave the top alone, because this is already a 3, and multiply the bottom by a 3. This will give me 3x. But it has to be that one of them is positive and one of them is negative, so I'll use a negative 3 here. So what's my system now? The top line doesn't change. The bottom line is now negative 3x minus 27z equals positive 90. And here's my new system. So you can see that these are going to cancel out. And what do I get? Well, I get 8 minus 27, which is negative 19z, and 90 minus 14, which is 76. Divide both sides by negative 19, and we get z equals, oh, sorry, that's a negative 19 right there. We get z equals negative 4. Our first of the 3 variables, we found it. Okay? So we back up. Now that we know what z is, we come back, it's called back substitution, we come back to the last system that we solved here, and we plug in negative 4 for z. It looks like the bottom equation might be easiest to solve for x, so I'm going to use the bottom equation here because the x is already by itself. So I'm going to use, you could choose either one, it doesn't matter, but I'm going to plug z into the bottom equation, so I have x, which I'm looking for, plus 9 blank, that's where the z is going to go, equals negative 30. And like we said, z is negative 4. So this becomes x minus 36 equals negative 30. You just add 36 to both sides, and you're done for this one here. So x equals 6. Great, we have 2 out of 3 now. Z is negative 4, x is 6. We take those 2 variables, we go way back to the original problem now. I need to find y. So you could choose whatever one is easiest. What you're really going to do is just look at this. You know that x equals 6 and z equals negative 4. You're just going to say, all right, which one's going to give me my y the quickest? And it looks like the top one would definitely have been the easiest one because the numbers are small and you just plug in a 6 there, all right? So subtract 6 from both sides. This becomes 2y equals 6, so y equals 3. If y equals 3, what's your final answer? Well, it has to be all 3 letters in alphabetical order. In this case, it's x, y, z, so 6, 3, and negative 4. X, y, and z in an ordered pair. Well, ordered triplet, actually. And there it is. Okay, last example here. Unfortunately, all of my examples are using x, y, and z, but remember, any letters can be used, A, B, C, W, R, T, whatever. Just make sure your answer is in alphabetical order. So for this one, let's just look at the top 2 here. Actually, before we get into the top 2 and bottom 2, let's decide what of the 3 letters is going to be the easiest to get rid of. So the least common multiple for 4, 12, and 2 is 12. 12 goes into 12, 2 goes into 12, 4 goes into 12. How about for 6, 5, and 2? Well, the lowest number that 6 and 5 go into is 30. 2 goes into that 30, so we don't have to multiply by 2. It doesn't have to be 60. So you go 30. And then here we have 21 and 1 would be 21. So it looks like the x's would be the one I would go for here. The one with the lowest number that they all go into evenly. So let's split this up. We'll take the top 2 equations, put them over here, and the bottom 2 equations. So once again, the top 2 would be these 2 here. The bottom 2 would be these 2 here. And we've decided we're going to get rid of the x's because the least common multiple for the x's is the lowest. So let's go ahead and do that. How can I make both of these into the, well, first of all, what is the least common multiple with 4 and 12? It's 12. So I need them both to become a 12 so I can cancel them out. One of them negative, one of them positive, 12. Well, the bottom's already a 12, so I don't have to touch anything. But the top, I need to multiply by 3 to get this to become negative 12x. So let's do that. This becomes negative 12x minus 6y minus 3z equals 45. And the bottom is going to be the same as it was before. And you notice something. This cancels out. This cancels out. This cancels out. And these don't. Okay, if you're not paying attention, you might cancel these out. But this is all, everything on the left side here is gone. So that's 0. There's nothing left. And this is 90. Okay, they don't cancel out, so be careful. Just because they're the same number, they have to also be different signs. This is 3 times positive 15, which is positive 45. And we didn't touch the bottom, so this is still positive 45. So when you add them, okay, these cancel out, these cancel out, these cancel out, but these become 90. And you get something here, 0 equals 90. If you remember from the lesson on elimination or even substitution, if you get an answer that's impossible, this is completely false. 0 does not equal 90. This is impossible. Then there is no solution to the system. And since there's no solution with this, we don't even bother doing the rest of this. Okay? So to summarize, we'll just look at the notes right here. When doing a 3-line system, if you get an inconsistent result, such as 0 equals 5 or something like that, or in this case it was 0 equals 90, from any of the two lines, stop, there is no solution. Okay, we're done, so see you at the next video.
Check this.